Hey everyone, and welcome back to another deep dive. Today we're going to be talking about a pretty interesting problem in graph theory. It's called the unfriendly partition problem.
Yeah, so it's basically like you've got a graph, right?
Okay.
And we want to split all those dots into two groups. But here's the twist.
What's the twist?
Each dot should have at least as many connections to dots in the other group as in its own group. So it's kind of like, everyone wants to be in the out crowd. They want more friends on the other side of the fence than their own.
That makes sense.
And it's super fascinating because for graphs with like a ridiculously huge number of dots, like an uncountable number, we know it's not always possible.
Really?
Yeah. But when we're talking about graphs with the countable number of dots, well, that's where things get a little fuzzy. We still don't know for sure.
That's where the mystery lies.
Exactly.
Okay, well, to help us solve this mathematical puzzle, we're diving into a paper by Aharoni and Shelah titled Remarks on the Countable Case of the Unfriendly Partition Problem.
Right. This paper dives into a very specific scenario where we can guarantee these unfriendly partitions exist.
Cool. So before we get ahead of ourselves, let's define some terms. First up, we've got graph coloring.
Oh yeah, graph coloring. Think of it like dividing our dots or vertices into two teams. Each team gets its own color, but not actual colors, more like labels, zeros and ones.
Right.
And the aim is to create what we call an unfriendly coloring, which basically means each vertex has at least as many connections to vertices with the opposite color as in its own group.
So like making sure everyone feels a little outnumbered by their friends from the other team.
Exactly.
I like that analogy. And what about these neighborhoods they keep mentioning? What's that all about?
Yeah. A vertex's neighborhood is just all the vertices directly connected to it, like your close circle of friends in a social network.
Makes sense. Okay, so an unfriendly coloring ensures that every vertex has more friends from the other color group in its neighborhood than its own. Now, what about those induced subgraphs?
Oh, an induced subgraph is just a smaller graph within the larger one. You pick some vertices and then look at all the connections between just those vertices.
Got it. So it's like zooming in on a particular clique within the network. Okay, that makes sense.
Yeah.
Now, what about alternating rays? Those sound a bit more complicated.
Yeah, so an alternating ray is a path that goes on forever, passing through tons of vertices.
Okay.
But the key here is it has to alternate between vertices with a finite number of connections, we call that finite degree, and vertices with an infinite number of connections, infinite degree.
So it's like a path that keeps switching between ordinary folks with a small number of friends and these superstars with a massive following.
Yeah, that's a great way to think about it.
Cool. Now, I'm curious about the main result of the paper theorem 1.1. What does it tell us about these unfriendly partitions?
Well, it states that any countable graph that doesn't have these alternating rays we just talked about can be partitioned in an unfriendly way.
Hold on, let me get this straight. They're saying that as long as we don't have those infinite paths that bounce between popular and unpopular vertices, we can always create these awkward divisions.
Precisely. So the presence or absence of those alternating rays is crucial in determining whether a graph can even have an unfriendly partition.
Wow, that's pretty significant. But how does this theorem relate to previous research on the unfriendly partition problem? I mean, haven't other mathematicians already looked at this?
Oh yeah, definitely. This theorem actually builds upon a lot of existing research. For instance, Aharoni, Milner, and Prikry. They showed that any countable graph with just a finite number of vertices with infinite degree, meaning there's a limit to the number of superstars in the network, always has an unfriendly partition.
So this new theorem basically expands on that. It's saying that even with an infinite number of superstars, as long as they're not organized in that specific alternating ray pattern, we can still find an unfriendly partition.
Precisely. It generalizes the previous result, and it also builds on work by Bruhn, Diestel, Georgakopoulos, and Sprüssel, who looked at rayless graphs to graphs without any rays at all.
Rayless graphs, so like networks with no paths that go on forever.
Exactly. And what Bruhn and their team found was that these rayless graphs always have unfriendly partitions. But Aharoni and Shelah take it further. They show that even if you do have rays in your graph, as long as they don't connect to vertices of infinite degree in that specific alternating pattern, the superstar ordinary folk dance, we can still find those unfriendly partitions.
So it's not just the presence or absence of rays, but how those rays interact with those superstars in our network.
Exactly. And the really cool thing about Theorem 1.1 is that it covers situations that previous research didn't, like graphs where each ray only goes through a limited number of vertices with finite degree. That's highlighted in Corollary 1.2, which comes directly from their main theorem.
So even if we have rays wandering through a bunch of ordinary folk, as long as they don't get caught in an infinite loop with those superstars. We can still split the graph in that awkward, unfriendly way.
Yep. And you know what's even more amazing?
What's that?
This theorem, when combined with another important result by Berger, gives us a pretty comprehensive understanding of when we can find unfriendly partitions in countable graphs.
Oh, wow. Tell me more about Berger's work.
Well, Berger focused on graphs that don't have what we call subdivisions of infinite cliques, which are these incredibly dense, tightly knit groups of vertices where everyone knows everyone else.
So like those ultra-exclusive clubs in the math world.
Exactly.
Okay, so between this new theorem, the findings on graphs with a limited number of superstars, the research on rayless graphs, and Berger's work on avoiding those super dense cliques, we're starting to get a clearer picture of when those elusive, unfriendly partitions actually exist. It's like we're piecing together a giant puzzle.
That's a great way to put it. And Aharoni and Real, they've given us a crucial piece of that puzzle.
Now I'm dying to know how they proved this theorem. What kind of math wizardry did they use?
Well, to get there, they use a powerful concept called normal spanning trees. They're really handy for understanding countable graphs.
Normal spanning trees. Remind me what those are again.
Okay, so think of a spanning tree like a simplified skeleton of our graph. It connects all the vertices without making any loops.
Right.
And it's considered normal if for every connection in our original graph, you know, the two dots, it connects those two dots, are either on the same branch of the tree, one is above the other, or they share a common ancestor.
So it's like creating a family tree for all the connections in our graph, right?
Wow.
And a normal spanning tree makes sure that all the connections respect that family hierarchy.
Exactly.
Got it. But how do these normal spanning trees help with the proof?
Well, the authors use them as a framework for constructing those unfriendly partitions.
Step by step, like building with Legos.
Yeah, they start with a small part of the graph, and then they just keep extending the partition carefully, making sure it stays unfriendly at every step.
So they're not trying to partition the whole graph in one go. They're strategically working piece by piece, gradually expanding their reach. Clever.
It is. And another tool they use is the idea of partial colorings. It's like coloring in a giant picture, but only filling in certain sections at a time.
So they're not coloring the whole graph at once. Instead, they're strategically coloring bits and pieces and expanding from there.
Yeah.
I like it.
Yeah. It lets them play around with different arrangements and tweak things before they commit to a full coloring.
Okay, so they're using normal spanning trees to create a sort of roadmap for their coloring. And then they're using partial colorings to carefully explore different options. I'm following so far. What else?
They also use something called strongly maximal colorings. You remember how we talked about unfriendly colorings at a vertex where a vertex has more friends from the other group than its own?
Yeah.
Well, a strongly maximal coloring takes it up a notch. It's not just unfriendly at one vertex. It's unfriendly at every vertex within a specific part of the graph.
Interesting. Why is that important for the proof, though?
Because these strongly maximal colorings are really closely connected to unfriendly partitions. By showing that these strongly maximal colorings exist under certain conditions, they can then prove that unfriendly partitions also exist.
I see. They're like stepping stones leading to the final goal of proving those unfriendly partitions.
Right.
So how do they prove the existence of these strongly maximal colorings?
That's where the lemmas and corollaries come in.
Lemmas and corollaries.
Think of lemmas as like mini theorems. They prove a specific part of the puzzle.
Okay.
And corollaries are basically conclusions we can draw from those lemmas. They add more detail and insight to those smaller results.
So it's like they're building a house brick by brick, with each brick being a lemma or corollary that contributes to the overall structure of the proof.
Exactly. And some key bricks in their proof are lemma 2.1 and its corollary 2.2. These show how you can adjust a coloring, you know, like rearranging things a bit to get closer to a strongly maximal coloring.
So they're essentially providing a guide on how to tweak things to make them work.
Precisely. Then we have lemma 2.3 and its corollaries 2.4 and 2.5. These focus on manipulating those partial colorings, allowing them to handle specific scenarios and keep the unfriendliness of the coloring intact as they expand it.
So they've developed a whole toolkit for crafting these unfriendly partitions, using each tool to address specific challenges in the proof.
Very cool.
But I'm also eager to hear about the proof itself. How do all these pieces fit together to show that countable graphs without alternating rays always have unfriendly partitions?
That's a great question. That brings us to their proof of Theorem 3.1, which is actually a slightly stronger version of their initial result.
Oh, okay. Tell me more about this supercharged theorem.
The proof uses induction. Think of it like climbing a ladder, each rung representing a more complex graph.
Got it.
And the trick to climbing this ladder is using the T-rank of the graph.
Mm.
It's basically a way to measure how complex the structure of the graph is. You know how we were talking about the family tree of connections?
Yeah.
The T-rank tells us how many generations there are in that hierarchy.
So a graph with a low T rank has a simpler family tree, while a graph with a high T rank has a more complex one.
You got it. And the authors use this T-rank to break down their proof. They start by proving that the theorem holds for graphs with a T-rank of 0, then use that to prove it for T-rank 1, and so on.
It's a classic divide and conquer strategy. But what about those base case graphs, the ones with a T-rank of 0? What do those look like, and how do they prove the theorem for those?
Well, a graph with a T-rank of 0 is either what we call locally finite or a left-null regular. A locally finite graph is one where every vertex only has a finite number of connections.
So it's like a well-behaved network where everyone only has a limited number of friends.
Exactly. And a left-null regular graph is one where every vertex has an infinite number of connections. It's like a network full of superstars, each with a massive following.
Okay, so we've got those two extremes. How do they prove theorem 3.1 for these base case graphs?
For locally finite graphs, they rely on a previous result. Lemma 2 from Aharoni, Milner, and Prikry's work. It gives them a shortcut to show the existence of strongly maximal colorings and therefore unfriendly partitions for those simpler graphs.
So they're building on prior research to lay the foundation for their own proof. That's smart. What about the left null regular graphs?
For those that get a little more hands-on, they build the unfriendly partitions step by step using a greedy algorithm.
A greedy algorithm? What's that?
Imagine picking teams for a game. You always choose the best player available at that moment without really thinking about the long-term strategy.
So a greedy algorithm basically just focuses on making the best choice in the moment, hoping it leads to a good outcome overall.
Yeah, exactly. And in this case, their algorithm is picking colors for the vertices one by one, trying to maximize the awkwardness at each step until the whole graph is colored.
So they've got the base cases down graphs with a T rank of 0. But how do they move up to prove the theorem for higher T ranks?
That's where the real fun begins. That's where we get into the inductive step. But I think that deserves its own conversation.
Yeah, let's take a break and come back to tackle the heart of their proof. Okay, so we're back and ready to tackle the heart of Aharoni and Shelal's proof, the inductive step. This is where they show how their result works not just for those simple base cases, but for much more complicated graphs, right?
Exactly. And it all hinges on those T ranks we talked about, remember? The higher the T rank, the more complex the graph's structure.
Right, like a more intricate family tree of connections.
And the inductive step basically proves that if the theorem works for graphs with a certain T rank, it must also work for graphs with a T rank one step higher.
So it's like saying, hey, we've already conquered all the lower levels of this math tower. Now let's show we can conquer the next level too.
Precisely. So they start by assuming the theorem holds true for all graphs with a T rank less than some value, let's call it alpha.
Okay.
Then they take a graph G with a T rank of alpha and try to prove that it also can be partitioned in that unfriendly way.
Makes sense. So where do they begin?
Well, the first scenario they tackle is when the root of our normal spanning tree, remember that's like the top of our family tree, has a finite degree, meaning it only has a limited number of connections.
Okay, so we're focusing on a specific type of graph within this higher T rank level. What makes this case interesting?
What's interesting is that if the root has a finite degree, there must be vertices further down in the tree structure that have an infinite degree. It's like having ancestors with smaller families and descendants with much larger ones.
I see. So we have a mix of ordinary folk and superstars within this family tree. How do they handle that?
They start by finding the vertices in G that have an infinite degree and are closest to the root. Let's call this set S. These are like the first generation of superstars in our graph.
So they're zeroing in on those key players, those vertices, with a lot of connections.
Exactly. And they start by coloring those vertices in and around set S, ensuring that the coloring is strongly maximal in that region.
Right, so creating those awkward social divisions within that crucial part of the graph. What's next?
Well, here they use the inductive hypothesis. They know that the subgraphs below those vertices in set S have a lower T rank, right?
Right, because we're assuming the theorem holds true for all graphs with a lower T rank.
Exactly. So they know those subgraphs can be colored in a way that satisfies the theorem. And then they cleverly stitch those pre-colored subgraphs together, carefully extending the coloring upward while making sure it stays strongly maximal and unfriendly at those vertices with infinite degree.
So they're using what they've already proven about those lower-level subgraphs to help them color this more complex graph.
Clever.
It is. But it gets trickier. They have to make sure everything stays consistent and unfriendly as they connect those subgraphs to the rest of the graph.
I can imagine that takes some careful maneuvering. But what happens if the root of the normal spanning tree itself has an infinite degree? Does that throw a wrench in their strategy?
It definitely adds another layer of complexity. If the root itself has an infinite degree, we can't rely on those closest vertices with infinite degree to get started, because now the root is a superstar. Right. It's like the head of the family is the most popular person in the network. So how do they adjust their approach?
Well, instead of looking at vertices with infinite degree, they focus on those with finite degree, particularly those closest to the root.
Interesting. So they're kind of flipping the script, focusing on the ordinary folk instead of the superstars to kick things off.
Exactly. And they do this because the subgraphs stemming from those finite degree vertices, their descendants have lower T ranks.
Ah. So once again, they can use what they already know about those simpler subgraphs thanks to the inductive hypothesis.
Precisely. They create a buffer zone around the root using those finite degree vertices and then extend the coloring outward from there.
Okay, so they've got strategies for when the root has a finite degree and for when it has an infinite degree. But I imagine it doesn't always fit neatly into those two categories. What about cases where you've got superstars with infinite degrees all over the graph, not just near the root?
That's where their case-by-case analysis comes in. They've identified specific situations that can arise, each requiring a slightly different tactic.
Can you give me some examples of these tricky scenarios?
Sure. One scenario is when a vertex with infinite degree has infinitely many children, vertices directly connected to it that are one level down in the tree, and all those children have finite degrees.
So it's like a superstar with a massive following of ordinary folk. How do they deal with that?
They carefully look at the connections between that superstar vertex, its children, and the rest of the graph, and they figure out how to assign colors to make sure the unfriendliness condition still holds true even in that messy situation.
Makes sense. And I'm guessing they have strategies for other weird situations too, right?
You bet. They address cases where a vertex with infinite degree has tons of connections to another vertex further down the tree, cases where it's surrounded by vertices that are already colored, and even cases where it's got a mix of children with both finite and infinite degrees.
Wow, it sounds like they've really covered all their bases. It's amazing how they break down this complex problem into these manageable pieces, addressing each challenge with such precision.
It really shows their deep understanding of graph theory and how to work with these intricate structures.
I'm starting to feel a bit overwhelmed by all the details, though. Is there a way to step back and appreciate the bigger picture? What are the key takeaways from this inductive step?
Yeah, it's easy to get lost in the weeds. The main point is that no matter how complex the graph, no matter how many generations are in that family tree, Aharoni and Riel have a method for constructing an unfriendly partition.
So they're basically saying we've got a recipe that works and it can handle any level of complexity.
Exactly. It all comes down to their clever use of those normal spanning trees, the flexibility of partial colorings, and the strategic use of strongly maximal colorings.
It's like they've built this powerful mathematical machine with each part working together to achieve this specific goal.
That's a great way to think about it. And using this machine, they can methodically conquer each level of that T-rank ladder, proving that their theorem works for all countable graphs without alternating rays.
Okay, that's a pretty huge accomplishment. They've tackled those base cases and worked their way up through that intricate inductive step, showing just how powerful in general their method is. But there's got to be more to the story, right? What happens after they finish that inductive step?
That's a great question, and it leads us to their concluding remarks. That's where they tie everything together and highlight what their research really means. But before we jump into that final chapter, maybe we should take a quick breather and let everything sink in.
Yeah, we've covered a lot of ground. Those concluding remarks deserve our full attention. Okay, so we're back and ready to dive into those concluding remarks from Aharoni and Riel. This is where they wrap up their findings and give us the big picture takeaway, right?
Exactly. And you know what's really cool? They emphasize that their proof isn't just about proving that these unfriendly partitions exist. It actually gives us a way to construct them.
So it's not just a theoretical result. They've given us a practical tool that other mathematicians can use. That's awesome.
It is. It helps us understand the structure of those countable graphs so much better, especially the relationship between vertices with finite and infinite degrees.
It's like they've handed us a map for navigating the complex world of these mathematical dots and lines. So what else do they highlight in their conclusion?
They talk about how their work is a big step forward in our understanding of the unfriendly partition problem, specifically for countable graphs, a problem that's been puzzling mathematicians for ages.
So it's not just about solving one puzzle. They're contributing to a much larger story of mathematical exploration. That's pretty inspiring.
It is, and their work could lead to all sorts of new research, encouraging mathematicians to look at even more complex graphs and try to find even more general conditions for when these unfriendly partitions exist.
It's like they've opened up a whole new chapter in this ongoing investigation of the unfriendly partition problem. But I'm guessing they didn't solve everything right. There must still be some unanswered questions.
Oh, absolutely. They actually leave us with several open questions, which is great because it keeps the mystery alive.
Ooh, I love a good mystery. What are some of the questions they pose?
One of the biggest ones is, what does this research tell us about solving the unfriendly partition problem for all countable graphs? Their theorem focuses on those graphs without alternating rays, but what about the graphs that do have those infinite paths that keep switching between popular and unpopular vertices?
So they've figured out a piece of the puzzle, but there's still a whole lot more to explore.
Exactly. And they even suggest that there might be other structures besides alternating rays that prevent those unfriendly partitions from existing. It's like there are hidden traps in the mathematical landscape just waiting to be discovered.
So the search continues for those elusive structures that might throw a wrench in our attempts to create those awkward divisions. This has been an incredible journey. We've learned so much about the unfriendly partition problem, explored some groundbreaking research, and even uncovered some new mysteries to ponder.
It really highlights the beauty of mathematics, doesn't it? There's always something new to discover, always another layer to peel back.
Absolutely. And for our listeners who want to delve even deeper into this topic, where should they go?
Well, first and foremost, I'd recommend checking out Aharoni and Riel's paper, Remarks on the Countable Case of the Unfriendly Partition Problem. You can find it online, and we'll include a link in the show notes.
And don't forget about those mathematicians whose work paved the way for this breakthrough. Folks like Aharoni, Milner, Prikry, Bruhn, Diestel, Georgakopoulos, Sprüssel, and Berger. They've all made significant contributions to this area of research.
Yes, their work is essential reading for anyone who wants to really understand the history and evolution of this problem. And for those who are just starting to explore graph theory, there are some fantastic resources out there, both online and in libraries. It's a fascinating field with so much to offer.
Well, I think it's safe to say that we've all gained a new appreciation for the unfriendly partition problem. It's a testament to the power of mathematical thinking and the thrill of tackling those unsolved mysteries that keep us curious and keep us coming back for more.
It's been a pleasure exploring this topic with you and our listeners. Until next time, keep those minds sharp and keep exploring.
And keep diving, deep knowledge seekers. Welcome back to another deep dive. Today, we're tackling a really interesting problem. It's called the unfriendly partition problem.
Okay.
Specifically, we're going to be looking at it in countable graphs.
Sounds good.
And I have some excerpts here that you sent over from a 2024 paper by Aharoni and Riel.
Okay.
And I'm really eager to kind of break this down with you.
Yeah.
This problem's been around for a little while, right?
It has. It's been kind of a thorn in the side of graph theorists for a while. And, the funny thing is, it's so simple to state.
Right.
Can you split the vertices of a graph into two groups?
Okay.
So that each vertex has at least as many neighbors in the other group as in its own?
All right. So almost like they want to be with the other group more than their own.
Exactly. They're a little bit unfriendly to their own group.
Okay.
You could call it that.
All right. So, but it turns out that for graphs with like an uncountable number of vertices,
Right.
it's not possible.
For uncountable, it's a no-go.
A no-go. Okay.
But when you restrict yourself to countable graphs,
Okay.
things get a lot more interesting.
Okay. So that's what this paper's kind of focusing on, is that countable graph space.
Exactly. They really dig into that and
Okay.
give us some new insights.
Before we get too far into the weeds, I just want to make sure that we're using all the right terminology.
Sure.
Can you remind us what an unfriendly coloring is in this context?
Okay, so basically, an unfriendly coloring is, you've got your graph.
Yeah.
You assign two colors, let's say red and blue,
Okay.
to the vertices.
Mhm.
And each vertex, as much as possible, wants to have more neighbors of the opposite color than its own.
All right, so it's unfriendly to its own color in a way?
Yeah, exactly. Like a neighborhood where everyone wants to be different.
Gotcha.
Everyone wants to stand out.
Now, the paper really focuses on these graphs without a specific structure.
Right.
Call them alternating rays.
Mm-hmm.
Can you remind us what those are?
Yeah, so imagine, you have a path, an infinite path.
Okay.
Within your graph. That's a ray.
Okay.
An alternating ray is a special kind of ray.
Okay.
It passes through infinitely many vertices of finite degree, but also infinitely many vertices of infinite degree.
Okay, so it's going back and forth between like sparsely populated and densely populated.
Yeah, you got it.
Okay, interesting. All right, so
it's like it can't make up its mind.
Right, exactly.
Finite, infinite, finite, infinite.
So Aharoni and Real essentially show that if your graph doesn't have these alternating rays,
right,
then you can guarantee an unfriendly partition.
Right. That's the big takeaway.
Okay.
Their main theorem, Theorem 1.1, says exactly that.
Okay.
Every countable graph without these alternating rays can be split up unfriendly.
So this is a big step forward, right?
Huge. Because, there's been a lot of work on this problem before. Like, for example, Aharoni, Milner, and Prikry.
Okay.
They proved a similar thing, but only for graphs with like a finite number of vertices with infinite degree.
Oh, okay.
But Aharoni and Real, they're like, nope, we're going to tackle a much bigger class of graphs.
So they're generalizing it.
Generalizing, expanding our understanding. It's great stuff.
Okay, now I also noticed that they had a corollary 1.2,
right,
which felt like a really neat little puzzle piece to the bigger picture.
It is. It's a special case, but it's super interesting.
Right.
It says, if every ray in your graph, so think all the infinite paths, only contains finitely many vertices of finite degree, then boom, you've got yourself an unfriendly partition.
Okay.
It's like even if you have these infinite paths, as long as they eventually hit this kind of infinite hub, the unfriendly partition exists.
So it's kind of like a special case.
Exactly. A neat little consequence of their main theorem.
Okay, now I have to admit, when I was reading through their proof, I was a little bit intimidated because it's a lot of really ingenious but really complex.
It's dense. It's dense.
Where do they even begin to tackle this?
So they use a lot of cool tools, right? Building on previous work, one of the key tools is normal spanning trees.
Okay.
Jung, way back when, proved that every countable graph has one of these normal spanning trees.
Right.
And they're super useful for organizing the graph's structure.
Okay, so they're using this tree as like a
framework.
A framework, okay.
A skeleton to hang their argument on.
Gotcha. All right, and then they also use this idea of partial colorings, right?
Yes. Partial colorings, this idea was actually introduced by Neil just last year in 2023.
Wow, okay. Recent.
Very recent, yeah. And it's exactly what it sounds like.
Great.
You color some of the vertices, not all of them.
Right.
And Aharoni and Real use this in a really clever recursive approach.
Okay.
They build up their unfriendly partition bit by bit.
Okay, so almost like they're solving like a jigsaw puzzle, but they're only coloring some of the pieces as they go.
Yeah. Yeah, that's a great analogy. They're like, let's get this corner done, then we'll worry about that edge.
All right, that makes sense. And then they refine their approach even more with these ideas of strongly maximal and almost strongly maximal colorings.
Oh, yeah, those are mouthful, aren't they?
Yeah, those are.
But they're really about, in a finite graph, you have this idea of a max cut.
Okay.
You're trying to find a coloring that maximizes the number of edges between vertices of opposite colors.
Gotcha.
It's like, how much can we divide this graph?
So they're trying to create division.
Division, yeah. Maximize the unfriendliness as much as possible.
And then they use this lemma 2.1, to help them tweak these colorings to make them even more unfriendly.
Exactly. It's like they're fine-tuning the recipe.
Okay.
Lemma 2.1 gives them this very precise way to modify the coloring by focusing on specific vertices and their neighbors.
Before we get too lost in the details, what is the overall structure of their proof?
Okay, so it's inductive.
Okay.
Meaning they start with a base case.
And then show how to kind of extend it to more complex cases.
Okay.
But the really cool thing is they actually prove a stronger statement than Theorem 1.1.
Interesting. Okay.
They prove Theorem 3.1, which gives us even more information about the properties of the unfriendly partition.
So they squeezed out more information than they even set out to.
Yeah, they're overachievers.
That's great, but what is this Theorem 3.1 exactly?
So it says, given a countable graph without alternating rays.
Okay.
You've got your normal spanning tree for that graph, right?
Right.
And you have a stable partial coloring of some of the vertices.
Okay.
You can always extend that coloring to an unfriendly coloring of the whole graph.
Okay.
But, and here's the key, you do it while preserving certain properties.
So we need to know what a stable partial coloring is then.
Right, right. So stable basically means three things.
Okay.
First, it's defined within a specific subtree of our normal spanning tree.
Okay.
Second, it's strongly maximal within that subtree.
So you can't make it more unfriendly in that little section. Exactly. It's already as divided as it can be.
Okay.
And third, every vertex outside the colored section has only finitely many neighbors that are higher up in the tree structure than a specific point within the colored section.
Okay.
It's a bit technical, I know.
Yeah.
But basically, these properties ensure that the final coloring will actually be unfriendly.
Gotcha. So they're being very careful about how they're building this thing up.
Very careful, laying the groundwork.
So they have this stable partial coloring.
Yep.
And they have to extend it to the whole graph without messing things up.
Exactly. It's like a delicate balancing act.
And how do they do this?
So they break the problem down into cases,
Okay.
like a divide and conquer strategy. Each case addresses a different scenario within the graph.
So can you walk me through some of these cases?
Sure. So in case one, they look at what happens when the root of the spanning tree,
Like the very beginning.
the starting point, has a finite degree. They cleverly break the graph down into smaller subgraphs.
All right, so they're simplifying it.
Simplifying, focusing on bite-sized pieces.
Okay.
And each of these subgraphs is rooted at a neighbor of the original root vertex.
So they're like branching out.
Branching out, exactly. And then they can kind of recursively apply theorem 3.1 to each of these subgraphs.
Okay. What about the other cases?
Well, case 2 gets a little more complicated.
Okay.
They're dealing with a vertex that has infinitely many neighbors.
Okay.
But all those neighbors are already colored.
Okay.
So they have to be really careful about how they color that new vertex.
Right.
They use corollary 2.2 in this case to make sure the coloring stays almost strongly maximal.
Gotcha. And then cases 3, 4, and 5.
Right.
Those are all about different scenarios depending on how many neighbors a given vertex has
Exactly.
in the already colored part of the graph.
They're really covering all their bases.
So it seems like a really thorough, systematic approach.
Absolutely. They're leaving no stone unturned.
But how do they handle when they have to deal with infinity?
That's where things get really interesting. They use these things called limit ordinals, which are like, infinite numbers, but they're special. They allow you to describe what happens at infinity.
Right.
So their coloring process stays consistent even when they're dealing with infinite sets.
Okay, so even though they're dealing with these infinite things, they have a way to keep it all in check.
They've got it under control,
So they're extending the coloring in all these different cases, but how do they guarantee that the final result is actually unfriendly?
So that's where lemma 3.6 comes in.
Okay.
This is a really clever part of the proof. They set up a contradiction.
Okay.
Remember we said they're working with graphs with no alternating rays.
Right, right. That was our starting point. That was one of the assumptions.
So lemma 3.6 basically says if their final coloring, which they call subi sub, is not unfriendly, then there must be an alternating ray in the graph.
Oh, so if their solution fails, it means the graph breaks the rules.
Exactly. It violates our initial assumption.
Oh, that's clever. All right.
So by process of elimination, their coloring must be unfriendly.
Okay.
Otherwise, we have a logical contradiction.
Okay, so they're using the structure they're trying to avoid to prove that their coloring works.
Exactly. It's a really elegant argument.
Okay, and there's one last piece of their proof, proposition 3.7.
Right, so this is like the final quality check.
Okay.
They use it to confirm that their coloring, subi sub, is actually unfriendly at all the vertices with infinite degree.
So they're zooming in on the trouble spots.
Yep, those infinite degree vertices can be tricky.
Right.
But proposition 3.7 says, nope, everything checks out.
So they're making sure every detail aligns perfectly.
Exactly. They're very thorough.
That's good.
It's a really beautiful piece of work.
Well, I think we've earned a break after that.
I agree.
That was a lot.
A lot to unpack.
Very dense.
So we'll come back refreshed and talk about what all this means.
Sounds
kind of the broader implications of their findings.
Looking forward to it. So we've really been in the weeds there with that proof.
Yeah, we've been down in the nitty-gritty.
But it's clear that, Arichi and Riel have done some really impressive work. They've moved the needle on this problem.
What are the lasting implications of this? Like, what does it tell us about countable graphs
Right.
and the unfriendly partition problem as a whole.
Okay, so the big thing is they've given us this new lens
Okay.
through which to view countable graphs, right?
Yeah.
They've shown that the presence or absence of these alternating rays
Right.
can actually determine whether or not an unfriendly partition exists.
So it's like they found a key structural
It's
thing
a key characteristic, yeah.
that governs this whole problem.
Exactly. It's a game changer in a way.
And I imagine this has implications that go beyond just the unfriendly partition problem, right? Absolutely. Think about other areas of graph theory.
Okay.
Even things like computer science, network analysis.
Okay.
This kind of insight can ripple out.
Can you give us an example? Like, how would this play out in a real-world setting?
Sure. Imagine you're designing a communication network, right?
Okay.
Big network, lots of nodes, and you want to minimize interference.
Oh, yeah.
You can represent that network as a graph. The nodes are your vertices.
Right.
The connections are your edges.
Okay.
Now, this idea of an unfriendly partition,
Yeah.
it can actually guide you in how to divide those nodes into groups
Okay.
to minimize that signal overlap,
So it has applications in like signal processing and things like that.
It's all connected,
Yeah.
Abstract math can lead to very practical solutions.
What questions does this paper raise? Because it seems like it answers some, but then it also must open up some new questions.
Oh, for sure. Every good paper does that, right?
Right.
It's like closing a door, but opening a window. So one of the big questions now is, what about graphs with other forbidden structures?
Okay.
We know that no alternating rays means you're good.
Yeah.
You can find an unfriendly partition.
Right.
But what if your graph doesn't have certain types of cycles
Okay.
or other specific subgraphs?
Yeah. Could you use similar techniques to figure those out?
That's the million-dollar question. Can we adapt these tools?
So there's a whole world of possibilities just branching out from this one paper.
That's what's so cool about math. There's always more to explore.
Before we move on, I just want to go back to Theorem 3.1 for a second.
Okay.
I feel like when we went over it, we kind of glossed over some of the really subtle details of how they build that argument.
Yeah, we were kind of high level, weren't we?
Yeah, and I think to really appreciate their work, we need to look at the specifics of that inductive process.
Okay.
And how they use all these different lemmas to kind of establish their claims.
Good idea. Let's dive back in.
So let's start with the base case of their induction. What is that, and how do they actually establish it?
All right. So the base case is when the colored subtree, they call it subasub, is just the root vertex of the normal spanning tree, like the very beginning.
Okay.
So the stable partial coloring, subasub, is just assigning a color to the root.
Red or blue?
Exactly. Nice and simple.
So how do they go from that to an unfriendly partition of the whole graph?
They look at the degree of the root vertex, right?
Okay.
There are two scenarios.
Okay.
If the root has finite degree,
Okay.
they break the graph up.
Again.
Yep, divide and conquer into a bunch of subgraphs,
Okay.
each one rooted at a neighbor of R, and then they apply Theorem 3.1 recursively to each of those subgraphs.
Okay.
And they use Lemma 3.2 to make sure that they can combine all those colorings together nicely.
So Lemma 3.2 is kind of like the glue that holds it all together.
It's the magic glue, yeah.
Okay, what about when the root has infinite degree?
Then they use a different tool,
Okay.
Lemma 3.3. This one is awesome.
Okay.
It lets them partition the neighbors of R
Yep.
into two sets, A and B,
All right.
so that every vertex in A has infinitely many neighbors in B,
Okay.
and every vertex in B has almost all its neighbors in A.
Yep.
It's a very specific kind of split.
Right.
But it lets them construct an unfriendly partition of the whole graph directly, just from that one split.
So they have these two lemmas, 3.2 and 3.3,
Oh.
kind of like specialized tools for each scenario.
Exactly. The right tool for the right job.
All right, that makes sense.
Gotta love a good lemma.
Now let's move on to the inductive step.
Okay.
What happens when the colored subtree, tuba sub,
Yeah.
is not just a single vertex?
Things get a bit more hairy.
Yeah.
They actually break it down into 5 separate cases.
Jive.
Yeah, they're thorough.
Okay, can you walk me through those?
So each case deals with a different type of vertex, V,
Great.
that they want to add to the colored subtree. And they have to be careful because they need to make sure the coloring stays stable.
Right.
So in case 1, they're looking at a vertex V with finite degree,
Right.
similar to the base case.
Yeah.
They break the graph up into smaller subgraphs rooted at the neighbors of V
Okay.
and use the induction hypothesis to
Oh.
extend the coloring.
So they're kind of doing that recursive thing again?
Recursion all the way down, yeah.
Okay, case 2.
Case 2 is where V has infinitely many neighbors,
Okay.
but they're all already colored.
Oh, okay.
So they have to be really careful here.
Right.
They use lemma 2.2.
Okay, the tweaking lemma.
The tweaking lemma, exactly, to make sure the coloring stays good.
Okay.
Case 3 is kind of similar.
Okay.
But now V has almost all its neighbors colored except for a finite number.
Okay.
Again, lemma 2.2 to the rescue.
They seem to use that one a lot.
It's a good lemma, versatile.
Okay, what about case 4?
Case 4 is interesting
Right.
because now V has infinitely many neighbors, but in the uncolored part of the graph.
Oh, okay, so it's like reaching out into the unknown.
Exactly, and this is where they introduce this idea of stable colorings.
Okay, what's that?
It's like a super-powered version of stable.
Okay.
Not only does it have those 3 properties we talked about before,
Right.
but it also has this extra condition.
Okay.
If V is colored red, let's say, it has to have infinitely many red neighbors within the already colored subtree, subasub.
So it's kind of like, even though it's reaching out, it still has to have a strong connection back to its own color.
Exactly. It can't just be off on its own.
All right, so it's a way to keep it grounded.
Grounded. Yeah, that's a good way to put it.
And then case 5.
Case 5 is all about successor vertices.
Okay.
Kind of a technical detail, but again, lemma 2.2 helps them out.
It's like their Swiss Army knife of lemmas.
It really is. It's a good one.
Okay, so they've accounted for all these different cases.
Yeah.
And shown how to extend the coloring in each one.
They're meticulous, those two.
Yeah. Now, what about those limit ordinals? We talked about them a little bit earlier.
Right. The infinite stages.
Where do they fit into all of this?
So they come into play when you have to construct subasub.
The colored subtree.
Yeah, in infinitely many stages.
Okay.
You can't just rely on the previous step anymore.
Right, because there's infinitely many steps.
You need a way to combine all the information from the previous steps.
Okay, so it's like they're building an infinite tower, and they have to make sure each floor is connected to the one below it.
Yeah, it's a good analogy.
Okay.
So at each limit ordinal, they define the coloring, subasub,
Okay.
by looking at all the colors assigned in the previous stages.
So they're kind of taking a snapshot at infinity.
Exactly. And they prove that this limit coloring is still stable.
So it doesn't fall apart when you reach infinity.
It holds together. Yeah, that's the magic.
Now, we've talked a lot about how they construct this partition, but how do they actually prove that it's unfriendly?
Right. That's the crucial part.
Yeah.
So they use lemma 3.6.
Okay.
To set up this really clever contradiction. Remember we said they're assuming no alternating rays in the graph.
Right, the forbidden structure.
Exactly.
Okay.
So lemma 3.6 basically says that if their final coloring, pseudosub, is not unfriendly, then there must be an alternating ray somewhere.
So if they're wrong, the graph is wrong.
Exactly. It's a beautiful contradiction.
So their coloring has to be unfriendly, otherwise the whole thing falls apart.
The logic is airtight.
Okay. And then there's proposition 3.7.
Right, the final check to make sure that subasub is actually unfriendly at all those infinite degree vertices.
So they're double checking those trouble spots.
Always got to be careful with infinity.
Right.
But proposition 3.7 gives them the green light.
So they've really dotted all their I's and crossed all their T's.
They're very thorough. It's a very satisfying proof.
I agree. It's really impressive how they've woven together all these different pieces.
Yeah, it's a masterpiece of mathematical reasoning.
I feel like I have a much deeper appreciation for their work now.
Me too. It's really elegant.
I think we should take a little pause here, though.
Okay.
Let all this sink in a bit.
Sounds good. Let's gather our thoughts.
And then we'll come back and talk about the bigger picture.
Looking forward to it.
So we've been really digging into the mechanics of Aharoni and Riel's proof.
Yeah, we've gone pretty deep.
And it's clear that they made, really substantial progress on the unfriendly partition problem.
Yeah, for sure.
But I've been thinking, as we've been talking about it, we're using all these words and these analogies.
Right.
But what about like the math, like the formal notation?
Yeah, that's important too.
How do they actually express these ideas in their paper?
So they use a lot of set theory, right, and functions to really make things precise.
Remind me how that works.
Okay, so like for the unfriendly coloring, for example, they represent the two colors as the set, 0, 1, and then a coloring, they call it C, is a function that maps each vertex to one of those colors.
So it's like assigning a number.
Yeah, like a label based on the color.
Gotcha. And then how do they express that condition of being unfriendly at a vertex?
So they use inequalities, right?
Okay.
And this idea of cardinality, which is just a fancy way of saying like the size of a set.
Okay.
So for a vertex V, they look at its neighbors, all of them. That's NV.
Okay.
And then they split those neighbors up into two sets.
Okay.
N sub 0 sub V, those are the neighbors colored 0.
Okay.
And N sub 1 sub V, the ones colored 1.
Okay, so they're dividing them based on color.
Exactly. And the coloring C is unfriendly at V.
Okay.
The size of N sub CV sub V,
Okay.
which is the set of neighbors with the same color as V,
Right.
is less than or equal to the size of N sub 1 CV,
Okay.
the neighbors with the opposite color.
So they're formally comparing the sizes of those two groups of neighbors.
That's exactly it.
Okay.
They're capturing that idea of wanting more neighbors of the opposite color.
Okay, that makes sense. And what about alternating rays? How do they define those formally?
So a ray, they call it R,
Okay.
is just an infinite path.
Yeah.
You know, V sub 0 sub, V sub 1 sub, V sub 2 sub, and so on.
Yeah, like an infinite chain.
Infinite chain connected by edges.
Okay, and then how do they say that it's alternating?
So they use the degree of the vertices, right?
The number of connections.
Exactly. So an alternating ray has to have infinitely many vertices with finite degree.
Okay.
And also infinitely many vertices with infinite degree.
Okay, so it's going back and forth between those two.
That's the key, that back and forth pattern.
It's so interesting how much information they can pack into a single mathematical statement.
It's pretty amazing, isn't it?
Yeah.
The power of notation.
And that's just, like the tip of the iceberg.
Yeah.
Use all sorts of cool math throughout the paper.
Ordinals, set theory, you name it.
I have to admit, though, those ordinals still kind of trip me up a bit.
Oh, yeah.
Yeah, can you remind me again why they're so important here?
So remember, ordinals are like an extension of the natural numbers.
Okay.
But they let you count past infinity.
Okay.
So you have 0, 1, 2, all the regular numbers.
Mm-hmm.
But then you have, ooh, that's the first infinite ordinal.
Okay.
And then O plus 1, O plus 2, and so on.
So it's like levels of infinity.
Yeah, exactly. And Aharoni and Real use them to label the stages of their construction.
Okay.
Because they have infinitely many steps.
Right.
So they need a way to keep track of where they are.
Okay, so like suba sub is the colored subtree.
At stage
away, okay.
And suba sub is the coloring at that stage.
It's like a timestamp almost.
Yeah, like a marker.
Okay, so those subscripts are actually telling us something important about the order.
Exactly. They're not just random symbols.
Okay, that makes me feel a little better about that.
Good. It all makes sense in the end.
Well, I have to say, this has been a really rewarding deep dive. I feel like I have a much better understanding of the unfriendly partition problem now.
And a deeper appreciation for the beauty of math, right?
Definitely. It's amazing how elegant it all is.
To anyone listening, if you want to learn more, I highly recommend checking out the paper itself.
Yeah, it's definitely worth a read.
It's challenging, but it's so insightful.
And even if you don't understand everything at first,
that's okay.
Take your time, break it down, look up some definitions.
The journey is part of the fun.
That's a great point. The learning process itself is really rewarding.
Exactly. And who knows, maybe this will inspire some of you to explore graph theory even further.
There's so much out there to discover.
The world of math is endless.
Well, on that note, I think we've reached the end of our deep dive.
A successful deep dive, I'd say.
We hope you enjoyed it, and we'll see you next time on the deep dive.
Until then, happy mathing.
Welcome back to the deep dive. Today, we're going to be diving into some exciting new research in graph theory, specifically the unfriendly partition problem now. This problem has been around for a while, and it asks a deceptively simple question. Can we always split the vertices of a graph into two groups so that every vertex has at least as many neighbors in the other group as in its own?
It's a deceptively simple question that leads to some surprisingly complex mathematics.
Exactly. And while the problem has been solved for general graphs, spoiler alert, the answer is no. The countable case is still open. We've got excerpts from a brand new 2024 paper by Aharoni and Real, and let me tell you, it's a dense one. Luckily, I've got an expert here who can walk us through the nitty-gritty.
Happy to help navigate this mathematical maze.
So, before we get lost in the weeds, let's start with the basics. Can you remind us what an unfriendly partition is, formally speaking?
Absolutely. Formally. An unfriendly partition of a graph is a coloring of its vertices. Using just two colors, we can represent them as 0 and 1. So we have a function denoted as C that maps each vertex of the graph, VG, to one of these colors, which we denote as 2, representing the set 0, 1. Mathematically, it's written as CVGE2. Now, A vertex is considered unfriendly if it has at least as many neighbors with a different color as those with the same color.
It's like a mathematical popularity contest where you only win if you have more friends than the other group. But this has been a tricky problem for mathematicians.
It has. You see, initially, it was conjectured that every graph had an unfriendly partition, however. Back in 1990, Milner and Shelah disproved this conjecture with a clever construction using uncountable graphs.
Uncountable graphs always seem to complicate things. But the countable case is still open, which is where Aharoni and Real's research comes in. Their paper makes some significant progress, doesn't it?
It does. They've managed to prove that if a countable graph doesn't contain a specific type of infinite path, what they call an alternating ray, then it must have an unfriendly partition.
Okay, hold on. Alternating rays. Those sound pretty important. What exactly are they?
Imagine an infinitely long path in your graph. A ray denoted as R equals V0, V1, V2. This ray is considered an alternating ray if it passes through an infinite number of vertices of both finite degree, vertices with a limited number of connections, and infinite degree, vertices with infinitely many connections.
So it's like a path that keeps switching between neighborhoods with a finite number of houses and neighborhoods with an infinite number, never settling on one type.
Precisely. And Aharoni and Real show that the presence of these alternating rays is a key obstacle to guaranteeing an unfriendly partition.
That's fascinating. It seems like they've identified a critical structural property of graphs that determines whether or not an unfriendly partition exists.
Exactly. And their work actually builds on and generalizes some important previous findings in this area. For instance, Aharoni, Milner, and Prikry had proven the existence of unfriendly partitions for graphs with only finitely many vertices of infinite degree.
So, if most of your vertices have a limited number of connections, you're good to go.
Right. But what Aharoni and Rel have done is provide a more comprehensive solution. Their result not only covers the case of finitely many infinite degree vertices, but also encompasses cases where you might have infinitely many vertices of both finite and infinite degree, as long as you don't have those troublesome alternating rays.
It sounds like they've unified and extended our understanding of this problem significantly now. I know they use some pretty heavy mathematical machinery in their proof. Can you give us a sneak peek at some of the tools they employ?
Of course. Two key concepts they rely on are normal spanning trees and strongly maximal colorings.
Okay. Those sound a bit intimidating. Can you break those down for us?
Certainly. Let's start with normal spanning trees. Imagine you have a tree that spans your entire graph, meaning it connects all the vertices without forming any cycles. Now, this tree becomes normal if for every edge in your original graph, the endpoints of that edge are comparable in the tree's hierarchy.
Comparable in the tree's hierarchy. It's like a family tree.
Right.
Right.
Every connection in the graph has to respect the ancestral relationships within the tree.
Precisely. And this concept of a normal spanning tree is crucial because it provides a way to organize the graph's structure in a hierarchical manner, which is essential for Aharoni and Real's inductive construction of the unfriendly partition.
So it's like they're imposing order on the chaos of the graph. Now, what about those strongly maximal colorings? What are those all about? Think back to our definition of an unfriendly partition. We want each vertex to have at least as many neighbors with a different color as those with the same color. A strongly maximal coloring takes this idea a step further. It requires that no matter which finite set of vertices you choose, you can't make the coloring more unfriendly by simply flipping the colors within that set.
So you're saying it's like finding the most unfriendly coloring possible. A coloring where no small group of vertices can collude to become more friendly with each other.
Exactly. And this concept of a strongly maximal coloring turns out to be incredibly useful for constructing unfriendly partitions, as we'll see when we delve into their proof.
Okay. I'm starting to see how these seemingly abstract concepts are laying the groundwork for their proof. But I'm eager to hear more about how they actually put all these pieces together.
Me too. But I think we need to pause our deep dive here for now. There's a lot more to explore in their proof, and we wouldn't want to rush through the beauty of their argument.
You're right. We need to savor this mathematical feast. To our listeners, stay tuned for part 2 of our deep dive, where we'll unpack the intricate details of Aharoni and Real's proof and witness the birth of an unfriendly partition.
Welcome back to our deep dive into the unfriendly partition problem and Aharoni and Real's fascinating 2024 paper.
It's great to be back. Last time we left off talking about normal spanning trees and strongly maximal colorings. These concepts feel a bit abstract, and I'm curious to see how they connect to the actual nuts and bolts of the proof.
Absolutely. They're not just abstract notions. They form the foundation of Aharoni and Real's approach.
You mentioned that normal spanning trees help impose order on the graph, giving it a hierarchical structure. Can we dig a bit deeper into how that works?
Certainly. Remember, a normal spanning tree is essentially a tree that connects all the vertices of our graph without creating any cycles. What makes it normal is that every edge in the original graph has endpoints that are comparable in the tree's order. Think of it like a family tree, where every relationship in the graph has to respect the ancestry within the tree.
Right. So no rebellious edges connecting distant cousins. But how does this family tree analogy help with the unfriendly partition problem?
Well, it's all about creating a framework for their inductive construction. Aharoni and Real use this normal spanning tree to define a hierarchy of vertices, which they call the T-rank.
T-rank, is that like a popularity ranking within our mathematical family tree?
It's a great way to think about it. Formally, they define the T-rank of a vertex V as 0, O, ep, denoted as rank TV, 0, if all the vertices in its downwards closure, denoted by phi v, which includes all its descendants in the tree, of either finite degree or infinite degree. So everyone in each lineage is on the same page in terms of their connection count. Either everyone has a limited number of friends, or everyone's a social butterfly with infinite connections.
Say it's a homogeneous family. Either everyone's at every party, or everyone prefers quiet nights in. But what happens when we have a mix of finite and infinite degrees within a lineage?
That's where the T-rank gets more interesting. For instance, a vertex of 2v with infinite degree has rank TV, where a vertex is an ordinal number greater than 0 if all the finite degree vertices in its downwards closure have smaller ranks.
So it's a recursive definition. A vertex's T-rank depends on the ranks of all its descendants with finite degree. It's like a manager whose seniority is determined by the experience levels of their team.
Exactly. The same logic applies to vertices with finite degree. Their T-rank depends on the ranks of their infinite degree descendants. It beautifully captures this back and forth between finite and infinite degrees that's at the heart of the problem.
I'm seeing how this T-rank captures the essence of those pesky alternating rays we talked about earlier. If you have an alternating ray, it means you have this constant interplay between finite and infinite degrees that would make it impossible to assign a consistent T-rank.
You've hit the nail on the head. Aharoni and Real actually prove that if this recursive definition of the T-rank fails, meaning there's a vertex whose T-rank can't be determined, then the graph must contain an alternating ray. This ensures that in the graphs they're considering, those without alternating rays, the T-rank is always well-defined.
That's a clever way to guarantee that their construction works. So now we've got this hierarchy of vertices based on their T-rank. What do they do with it?
They use it to define the T-rank of the entire graph, denoted as rank TG, which is simply the T-rank of the root of their chosen normal spanning tree.
So the root vertex holds all the power. Its T-rank determines the fate of the entire graph.
Indeed. And they don't just pick any random normal spanning tree. They define the rank of the graph G, denoted as rank, as the minimum T-rank over all possible normal spanning trees for G. This ensures their construction is as efficient as possible.
Smart move. They're finding the most streamlined family tree possible.
Precisely. And with this carefully chosen normal spanning tree and its associated T-rank hierarchy, they're ready to launch into their inductive proof.
Okay, let's hear it. How does this induction work?
The base case, where rank G equals 0, is quite simple. Recall that this means all vertices in G have either finite or infinite degree. No mixing allowed.
Right. Everyone's either a social butterfly or a recluse, no in between.
Exactly. For graphs where all vertices have finite degree, they simply cite an existing result. Lemma 2 from Aharoni, Milner, and Prikry's 1990 paper, which guarantees the existence of a strongly maximal coloring, and hence an unfriendly partition for such graphs.
So they're building on the foundations laid by previous mathematicians.
Precisely. And for graphs where all vertices have infinite degree, they point out that a simple greedy algorithm can construct an unfriendly partition.
So the base case is taken care of. Now, I imagine the inductive step is where things get more intricate.
You're absolutely right. This is where the true beauty of their argument shines through. They assume that Theorem 3.1, which outlines the conditions for extending a predefined coloring, holds for all graphs with ranks strictly less than as, where as is some ordinal greater than 0 then. They demonstrate that it also holds for graphs with rank y.
Classic inductive reasoning. If it works for smaller cases, it must work for the bigger ones. But I'm guessing this isn't a simple copy and paste situation.
Not at all. The inductive step itself is divided into two main cases, depending on whether the root of their chosen normal spanning tree has finite or infinite degree.
Okay, so the strategy depends on whether the head of the family is a social butterfly or a bit more reserved.
Exactly. Let's start with the case where the root power has finite degree.
So, our root vertex prefers a smaller circle of friends. What happens next?
They cleverly define a set S, which consists of all the minimal vertices with infinite degree. Think of these as the up-and-coming social butterflies of the graph, those who haven't quite reached the top of the hierarchy but have a large network nonetheless.
The influencers on the rise. I like it.
A perfect analogy now. They use these minimal vertices with infinite degree to strategically break the graph down. They construct a subgraph H that contains all the ancestors of these influencers, including the influencers themselves, as well as the descendants' specific minimal vertices that are not ancestors of S.
So they're essentially creating a subgraph that includes the influencers, their entourage, and some additional vertices that are not connected to the influencers.
Exactly. And the beauty of this construction is that it guarantees that this subgraph H is locally finite, meaning all its vertices have finite degree.
They're isolating those troublesome infinite degree vertices into smaller, more manageable groups.
Precisely. And with H under control, they shift their focus to the remaining parts of the graph, the downwards closures of the minimal vertices that are ancestors of the influencers but are not part of S themselves.
These are like the subcommunities led by those up-and-coming influencers.
Exactly. And here's where the inductive hypothesis comes into play. Each of these subcommunities has a rank strictly less than Elio, allowing Aharoni and Real to apply theorem 3.1, the theorem they're proving, to each piece individually.
That's brilliant. They're breaking the problem into smaller puzzles that they already know how to solve.
Precisely. They use the inductive hypothesis to construct strongly maximal and unfriendly colorings for each of these subcommunities, carefully ensuring that these colorings agree with the predefined coloring on the finite graph K from the theorem statement, and with each other where they overlap.
So it's like solving a jigsaw puzzle, piece by piece, making sure the colors match the edges. But then comes the big challenge, merging all these individual solutions into a global one.
You've hit the nail on the head, and that's where those stable colorings come in.
Okay. I'm ready for a refresher on stable color.
Remember, stable colorings are special types of partial colorings defined on a subset of the graph's vertices. Denoted as D, they have those three key properties. Property S1. The domain D of the coloring can be split into two parts, a subset contained within the infinite degree vertices and the downwards closure of an anti-chain.
Anti-chain. It's like a group of individuals who share no common ancestor in our family tree analogy.
Exactly. Property S2. The coloring is strongly maximal within the downwards closure of that anti-chain, meaning we've maximized the unfriendliness within that specific region of the graph. Property S3. Vertices outside the domain of the coloring can only have finitely many neighbors above a given vertex in the anti-chain, so we're limiting the influence of those outside the stable zone.
It's all about carefully controlling the spread of unfriendliness as the coloring expands.
Precisely. Aharoni and Real prove several lemmas and corollaries that demonstrate how to construct and extend these stable colorings while maintaining all three properties. They essentially show that stable colorings act like the glue that binds the local solutions together, ensuring the resulting global coloring is still strongly maximal and unfriendly.
So it's like they're not just solving little puzzles, but also creating a framework that ensures all the puzzle pieces fit together seamlessly.
A perfect way to put it. And they use this technique to tackle both cases of the inductive step. The case where the root R has finite degree, which we just discussed, and the case where R has infinite degree, which involves a similar but slightly more intricate argument.
Amazing. So they have a unified approach for both scenarios.
They do. And by successfully navigating both cases of the inductive step, they prove theorem 3.1 for all countable graphs without alternating rays.
Wow. What a journey.
It is. But like any good deep dive, I think we need to surface for a moment to catch our breath. We've covered a lot of ground, and there's still more to explore in their proof.
You're right. We need a moment to process all this mathematical brilliance.
Mm-hmm.
To our listeners, join us for the final part of our deep dive, where we'll see how Aharoni and Real use these tools to conquer the final stages of their proof. Welcome back to the final part of our deep dive into the unfriendly partition problem. I'm still reeling from the ingenuity of Aharoni and Real's approach.
It's a remarkable piece of work, isn't it? They've woven together so many intricate concepts to create this elegant proof.
Exactly. Last time we left off talking about those stable colorings, and how they act as the glue that binds together the local solutions in their inductive construction. I'm eager to hear more about how they use these stable colorings to conquer the final stages of the proof.
Well, remember, the inductive step involves two cases, depending on whether the root of our chosen normal spanning tree has finite or infinite degree. We delved into the finite degree case in part 2.
Right, where they cleverly isolated those influencers, the minimal vertices with infinite degree, and broke down the graph into smaller, more manageable pieces.
Exactly. They used the inductive hypothesis to solve each of those pieces and then employed stable colorings to stitch them together.
Okay, that makes sense. But what happens in the other case, where the root of the normal spanning tree has infinite degree? How do they handle that scenario?
It's a bit more intricate, but the core strategy remains the same. Divide and conquer using stable colorings, in this case. They start by defining a special set M consisting of minimal vertices with infinite degree, whose downwards closure contains at least one vertex with finite degree.
So these are like influencers who have at least one recluse in their extended social circle.
A great analogy. Now, they use this set M to decompose the graph into smaller pieces. Each piece consists of the downwards closure of a vertex in M, denoted as V for V in M.
So each piece represents the social sphere of one of these special influencers.
Exactly. And here's where the inductive hypothesis comes into play again. Each of these pieces has a rank strictly less than Aharoni gamma, the rank of the original graph, because we've excluded the root vertex, which had infinite degree and therefore contributed to the overall rank.
So they've cleverly reduced the problem to a set of smaller subproblems, each with a lower rank.
Precisely. This allows them to apply Theorem 3.1 to each piece individually, constructing strongly maximal and unfriendly colorings that agree with the predefined coloring on the finite graph K and with each other where they overlap.
It's like they're recursively solving these social sphere puzzles.
Yeah.
Ensuring the solutions blend seamlessly where they intersect.
It's a perfect way to visualize it now.
Yeah.
Once they have these local solutions, they need a way to merge them into a global solution that covers the entire graph. And once again, they turn to those trusty stable colorings to do the heavy lifting.
I'm starting to appreciate just how versatile these stable colorings are. They're like the Swiss Army knife of unfriendly partition construction.
They truly are. Aharoni and Riel carefully demonstrate how to extend these stable colorings piece by piece, ensuring that all three properties are preserved at each step. They use a clever combination of lemmas and corollaries to establish specific rules for extending these colorings depending on the properties of the vertices being added.
It's like they're meticulously building a wall, brick by brick, making sure each new brick fits snugly and contributes to the overall stability.
You've got it. And they use this technique to handle both cases of the inductive step, whether the root has finite or infinite degree, demonstrating that in both scenarios. A stable coloring can be extended to cover the entire graph while preserving its crucial properties.
So, they've shown that as long as the graph avoids those troublesome alternating rays, a strongly maximal, unfriendly partition can always be constructed.
Exactly. They've successfully navigated both cases of the inductive step, proving Theorem 3.1 for all countable graphs without alternating rays.
What an incredible feat of mathematical ingenuity. I'm honestly a bit awestruck by the depth and elegance of their argument.
Me too. It's a testament to the power of abstract concepts like normal spanning trees, T-ranks, and stable colorings in solving seemingly concrete problems.
Absolutely. It feels like we've gone on a true mathematical adventure, exploring a hidden world of intricate structures and surprising connections.
And like any good adventure, it leaves us with new questions and a desire to explore further.
You're right. What are some of the open questions that this work sparks for you?
Well, one cool one that immediately comes to mind is whether their techniques can be extended to handle graphs that do contain alternating rays. Perhaps there are certain types of alternating rays that are tamer than others, allowing for unfriendly partitions under specific conditions.
That's a fascinating question. It's like asking if there are certain types of chaos that can still be reconciled with order in this mathematical world.
Exactly. And another question worth exploring is whether their approach can shed light on other open problems in graph theory. Perhaps the concepts of T-ranks and stable colorings have applications beyond the realm of unfriendly partitions.
It feels like they've given us a new set of tools to explore the vast landscape of graph theory.
They have, and I have a feeling that their work will inspire a wave of new research, pushing the boundaries of our understanding even further.
This has been a truly enlightening deep dive. A huge thank you to our expert for guiding us through this intricate mathematical terrain.
It's been my pleasure.
And to our listeners, thank you for joining us on this journey of mathematical discovery. We hope you've gained a deeper appreciation for the beauty and complexity of the unfriendly partition problem, and that you'll continue to explore the fascinating world of graph theory with us. Until next time, keep those minds curious. All right, so today we're taking a deep dive into a really fascinating area of graph theory. We're going to be talking about the unfriendly partition problem.
Yes, and we're going to be looking at a paper by Aharoni and Shelah, which offers some new perspectives on it.
Right, so we've got some excerpts from their paper here and some other related work. So maybe to start, can you just remind us what the unfriendly partition problem is?
Sure. So imagine you have a graph, which is basically a collection of points called vertices connected by lines called edges. And the unfriendly partition problem asks, can we always divide those vertices into two groups so that each vertex has at least as many connections to vertices in the other group as it does to vertices in its own group?
Okay, so more enemies than friends, essentially.
Exactly. And it's, it might sound simple at first glance, but it turns out to be a really tricky problem, especially when we're talking about countable graphs.
Right. Those graphs that have potentially an infinite number of vertices, but are still countable, like the natural numbers.
Precisely.
And this problem has been, sort of nibbled at around the edges for a long time now. There's been work on it for different kinds of graphs, but for countable graphs in general, it's remained unsolved. Mm-hmm. And Aharoni and Shelah, they're offering a solution for a certain type of countable graphs. Is that right?
Yes, that's correct. But maybe before we jump into their solution, it might be helpful to take a quick look at the existing work on this problem.
Yeah, that sounds good. Give us a little bit of the history.
So, as you mentioned, the unfriendly partition problem has been studied for a variety of different graphs. For example, way back in 1990, Milner and Shelah showed that unfriendly partitions are not always possible for uncountable graphs. So those are graphs that have a larger infinity of vertices than the countable ones.
Okay, so that kind of narrowed the focus a little bit to those countable ones.
Exactly. And then in 1985, Aharoni, Milner, and Prikry found unfriendly partitions for graphs with a finite number of vertices of infinite degree. So that's where you have a finite number of points, but each of those points is connected to infinitely many other points.
Okay, so we're starting to see some progress here, some specific cases where it does work.
Right. And then adding to that, in 2011, Bruhn, Diestel, Georgakopoulos, and Sprüssel showed that rayless graphs also have unfriendly partitions. And rayless graphs are graphs that don't have any infinite paths extending in one direction.
Oh, okay, so those infinite paths, like going off to infinity in just one direction.
Yes, exactly.
Okay, so bit by bit, people have been figuring out, okay, for this type of graph it works, for this type of graph it works. But Aharoni and Shelah are coming in with a bigger chunk of the problem solved. Is that right?
Yes, that's a good way to put it. They're introducing this really cool concept of alternating rays. An array, as we just discussed, is a path in a graph that goes on forever in one direction. Now, an alternating ray is a special kind of ray that passes through infinitely many vertices of finite degree and infinitely many vertices of infinite degree.
Okay, so it's alternating between those two types of vertices as it goes off to infinity. That's really interesting.
It is. And their big result, presented in Theorem 1.1 of their paper, is that any countable graph without these alternating rays does have an unfriendly partition.
Wow, so that's a really big step forward. It's like they've generalized a lot of those previous findings about specific types of graphs.
Yeah, exactly. It covers many of those previous cases as special instances.
That's really cool. So they've told us what they found.
Yeah.
But now I'm curious, how did they prove it? That's where the real meat of this is, right?
Absolutely. And their proof is actually really quite ingenious. They're combining some existing techniques with some new ideas, and it all hinges on this clever use of normal spanning trees.
Okay, normal spanning trees. Break that down for us.
So imagine a tree structure, with a root and branches that spans the entire graph, connecting all the vertices in a specific order. That's our normal spanning tree. It's a way to sort of impose some organization on the graph.
Okay, so it's like we're taking this potentially jumbled mess of vertices and edges, and we're kind of laying it out in a tree structure so we can see how everything connects.
Exactly. And once we have the structure in place, they use this idea of strongly maximal colorings as a kind of stepping stone to get to an unfriendly partition.
Strongly maximal colorings? What's that all about?
Well, think of it like this. You're trying to sort a big bag of marbles of different colors. A strongly maximal coloring is like you've gotten the colors roughly grouped together, but it's not perfect yet. Some marbles might be in the wrong group, but you're close.
Okay, so it's not a perfect unfriendly partition yet,
Yeah.
but we're getting there. But how do we know we can even get to a perfect partition? How do we know we can keep sorting those marbles until everything is in the right place?
That's where Lemma 2.1 comes in. It essentially says that if you start with a strongly maximal coloring and you change the color of just one vertex, the resulting coloring is still close to being strongly maximal. And this is true as long as the vertex you changed either has a finite degree or wasn't already unfriendly in the coloring.
So it's like we're making these little adjustments, like swapping marbles around. And as long as we're careful, we're always staying close to that roughly sorted state. But with infinite graphs, how do we know we'll ever actually finish sorting?
That's a great question. And it leads us to their proof technique, which is transfinite induction.
Transfinite induction sounds intimidating.
Well, think of it like climbing an infinitely tall ladder. You have to show that you can reach the first rung, and then that if you can reach any rung, you can also reach the next rung. Transfinite induction extends this idea to handle infinite processes.
Okay, so it's like a guarantee that we can keep climbing this ladder forever and still make progress.
Exactly. Now, their proof for Theorem 1.1 uses this transfinite induction to build up an unfriendly partition step by step. And the base case of their induction deals with these simpler graphs, like the locally finite graphs, where every vertex has a finite degree, or the ORed regular graphs, where every vertex has infinite degree. For those cases, finding an unfriendly partition is relatively straightforward.
Okay, so we've got our starting point, the first rung of the ladder. But then how do they handle the next steps, the more complicated graphs?
Well, for the inductive step, they have to show that if they can find an unfriendly partition for a certain part of the graph, they can then extend it to a slightly larger part. And this is where things get really detailed. They have to break down the graph into different cases based on its structure, and they have to very carefully extend the coloring while making sure it stays strongly maximal.
So it's like they're building this partition piece by piece very meticulously, always making sure it's so close to being unfriendly.
Yes, precisely. And one crucial part of this is lemma 3.3. It deals with the case where the root of our normal spanning tree, remember that's like the starting point of our tree structure, has a finite degree. And they use induction again here to show that we can extend the coloring in a way that keeps everything working nicely.
Got it. So like proving that we can add a new branch to our tree without messing up the existing structure.
Exactly. Now, the cases where the root has infinite degree are even more challenging, and the paper really digs deep into these cases, breaking them down into 5 separate subcases, each requiring its own special approach. It's like navigating through a complex maze.
A maze with infinitely many paths. How do they even keep track of everything?
Well, they have some tools to help them. One crucial one is lemma 3.6. This lemma is like a compass that prevents them from getting lost in the maze. It basically shows that if they can't extend the coloring any further using their defined strategies, then something must have been wrong with their initial assumptions about the graph.
Okay, so it's like a safety net to make sure they don't hit a dead end and get stuck.
Exactly. It guarantees that their construction process will always work. And eventually, after navigating through all these cases, they arrive at proposition 3.7, which is like the grand finale of their proof. It basically confirms that the coloring they've constructed really is unfriendly at all the vertices with infinite degree, just like their theorem says it should be.
Wow, so they've really built this up from the ground up, very carefully and meticulously, proving it every step of the way. Pretty impressive.
It really is. But there's one thing that still kind of boggles my mind. Like, we've talked about how they use this transfinite induction, right? But those limit ordinals, those points where we're basically dealing with infinity, how do they handle those? It seems like that could really throw a wrench in the works.
Yeah, you're right. That is a bit mind-bending. How do they make sure that what they've built up so far can smoothly transition into the infinite?
That's a great question, and it leads us to the next fascinating chapter of their proof, which we'll delve into in part 2 of our deep dive.
Welcome back. We're continuing our deep dive into Aharoni and Riel's proof for the unfriendly partition problem. And last time we left off talking about how they handle those limit ordinals, which is basically like dealing with infinity in the middle of this construction process.
Sure.
So can you maybe walk us through how they managed to pull that off?
Yeah, so limit ordinals are definitely one of the trickiest parts of the proof. Remember, we're building our unfriendly partitions step by step, kind of like climbing an infinite ladder. And those limit ordinals, they're like reaching those infinite mile markers along the way.
Okay, yeah, those points where we've kind of gone infinitely far, but we still have infinitely far to go.
Right, exactly. So at those points, we need to make sure that everything we've built up so far can be smoothly extended into the infinite. So when they reach a limit ordinal, let's call it alpha, they define the domain of their coloring at that stage, meaning the set of vertices we've colored so far as the union of all the domains of the colorings at previous stages, all those indexed by ordinals smaller than alpha.
So it's like we're taking all the colored pieces we've assembled so far and sort of gluing them together at this infinite meeting point.
Yeah, that's a good way to think about it. And then for those vertices in H, remember, those are the vertices that aren't tucked away nicely in the subtrees rooted at vertices in X. The coloring at stage alpha is defined by just taking the color assigned to that vertex at the earliest stage where it was colored.
So we're respecting the history, so to speak, keeping the colors we've already assigned. But what about those subtrees rooted at the vertices in X? How do they handle those at the limit ordinals?
So for each of those subtrees, they pick a representative coloring from a previous stage, one that already contains all the important information about that subtree's neighborhood.
So it's like taking a snapshot of the subtree's coloring at a point in time when we already knew everything we needed to know about its surroundings.
Exactly. And they choose a stage where the subtree's neighborhood hasn't changed since, so they can be sure that their color choices at the limit ordinal will still be consistent with everything that's come before.
Okay, so it's all about being very careful and strategic about how they stitch together these colorings at those infinite points.
Right, exactly. And by handling those limit ordinals in this way, they can be sure that their construction process continues smoothly, even when dealing with infinity.
That's really impressive. So they've managed to build up this coloring step by step, even through those tricky limit ordinals. But now we still need to make sure that this final coloring really does meet the requirements of an unfriendly partition, right?
Exactly. We need to make sure that every vertex, especially those with infinite degree, has at least as many neighbors in the other group as in its own group. And to do that, they've got to be really careful about how they handle the coloring of those H vertices we talked about earlier.
Right, those H vertices, the ones that aren't contained within those nice organized subtrees.
Exactly. Because those H vertices are kind of more exposed, they're more likely to end up with a lot of new neighbors as the coloring process goes on.
So a vertex that might have seemed friendly early on could suddenly become unfriendly as more and more vertices are added to its neighborhood.
Yeah, exactly. And that's something Arichi and Real have to anticipate and account for in their proof.
Okay, so how do they do that? How do they make sure that those H vertices end up on the right side of the partition, even with all those potential new neighbors?
Well, it comes down to how they choose the color for each H vertex when they first encounter it. They're not just trying to make it unfriendly based on its immediate neighborhood. They're also trying to predict how its neighborhood might change in the future.
Oh, so they're kind of playing this predictive game, trying to outsmart the evolving structure of the graph.
Right. They're analyzing the potential ways in which that vertex's neighborhood might grow, and then they're choosing a color that will give it the best chance of ending up with more enemies than friends, even if it gains a lot of new neighbors later on.
But how can they predict the future of the graph? It seems like that would be impossible.
Well, it's not about predicting the exact structure, but more about understanding the limits and the rules of their construction process. Remember, everything they do is designed to maintain stability and gradually build towards an unfriendly partition. So they're using their knowledge of those constraints to make smart decisions about coloring.
Okay, so it's kind of like they're setting up these safeguards to make sure that things don't go too far in the wrong direction, even as the graph keeps growing.
Yeah, that's a good way to put it. They're using their understanding of the process and the properties of stable colorings to guide their decisions and avoid those scenarios where a vertex suddenly gets overwhelmed with too many friends.
It sounds incredibly intricate, but I'm starting to see how it all fits together. They're really thinking ahead at every step, making these strategic choices to ensure that the final coloring will meet the unfriendly condition. But, speaking of thinking ahead, there's something we haven't talked about yet that seems really important. Like, we've seen how they handle those limit ordinals, those infinite steps. But what about those earlier steps, those successor stages where they're coloring one vertex at a time? It seems like those could potentially cause problems down the line, especially for those vertices with infinite degree.
You're right, that's a crucial point. Just because a vertex looks unfriendly at an early stage doesn't mean it will stay that way.
Yeah.
As the coloring progresses, it could end up with a lot more neighbors, and we need to be sure that it still has more enemies than friends in the end.
Exactly. So how do they handle that? How do they make sure those early color choices don't come back to bite them later on?
Well, that's something we'll delve into in part 3 of our deep dive. We'll see how they carefully analyze those successor stages and make sure that even those vertices colored early on will ultimately satisfy the unfriendly condition. It's a fascinating piece of the puzzle, and it really highlights the depth and the complexity of their work.
Okay, so we're back, and we're really getting down to the nitty-gritty of Aharoni and Rell's proof now.
Mm.
We've seen how they handle those limit ordinals, like those infinite checkpoints in their construction. But we left off with this question about those early stages, those successor stages where they're coloring one vertex at a time. How do they make sure that a vertex that looks unfriendly early on doesn't accidentally become friendly later as the graph keeps growing?
Yeah, it's a really subtle point, but it's super important to make sure that their construction is rock solid. Remember, we're dealing with infinite graphs here, so a vertex could potentially keep gaining new neighbors forever. And that means that even if it looks like it has more enemies than friends at some point, it could flip later on if it ends up with way more new neighbors in its own group.
Right, that makes sense. So they've got to somehow account for that possibility, even though they don't know exactly how the graph will evolve in the future.
Exactly. And the way they do that is pretty clever. When they color a vertex in H, those are the vertices that aren't neatly contained in the subtrees rooted at vertices in X. They don't just focus on its immediate neighborhood, they also consider how that neighborhood might change down the line.
So they're kind of anticipating those future connections, even though they don't know exactly what they'll be.
Yeah, precisely. They're looking at the potential ways that the vertex's neighborhood could grow based on the properties of stable colorings and the rules of their construction process. And they're using that information to choose a color that will maximize the chances of that vertex staying unfriendly, even if it gains a lot of new neighbors in the future.
Okay, but how do they even begin to analyze those potential future connections? It seems like there could be so many possibilities, especially with an infinite graph.
It's true, there are infinitely many possibilities, but they don't need to analyze every single one. They're using their knowledge of the constraints of the problem to narrow down the possibilities. They know that their construction has to maintain stability, and they know the general rules for how new vertices can be added. So they're essentially looking for the worst case scenarios, the ways in which the vertex's neighborhood could grow, that would be most likely to tip the balance from unfriendly to friendly.
Oh, so it's kind of like they're stress testing their coloring, trying to find the breaking points, and then reinforcing those points to make sure it holds up.
Exactly. They're identifying those potential weak spots and then choosing colors that will strengthen those areas, so to speak. They're making sure that even if the worst case scenario happens, that vertex will still end up with at least as many enemies as friends.
That's a really cool strategy. So they're not just coloring the graph, they're kind of playing this strategic game against the infinite possibilities of the graph's future.
Yeah, that's a great way to put it. It's like they're playing chess, always thinking several moves ahead. And because of their careful planning and foresight, they can be confident that their final coloring, COC, will truly be unfriendly at all vertices of infinite degree, even those that were colored at very early stages.
That's amazing. It really speaks to the power of their method and the depth of their understanding of this problem. So after this incredible journey through their proof, with all its twists and turns and careful considerations, what's the big takeaway? What have we learned from Aharoni and Rell's work?
Well, I think their work is a testament to the power of rigorous mathematical thinking. They've taken this really challenging problem, this problem that's been around for decades, and they've managed to make significant progress towards a solution. And they've done it by carefully building up their argument step by step, by using powerful tools like normal spanning trees and stable colorings, and by thinking very carefully about the potential pitfalls and how to avoid them. It's a really beautiful piece of work, and it shows what can be achieved when we combine creativity and rigor.
Absolutely. And I think it also highlights the beauty of graph theory itself, right? I mean, it's this field of mathematics that deals with these seemingly simple objects, points and lines, but it can lead to such deep and complex questions. And the answers to those questions, as we've seen with Aharoni and Rell's work, can be really elegant and surprising.
Definitely. And their work also opens up a lot of new questions, new avenues for exploration. It's like they've shed light on a new path through this complex landscape. And now it's up to other mathematicians to follow that path, to see where it leads, and to maybe even discover new paths of their own. That's what makes research like this so exciting. It's always pushing the boundaries of what we know.
That's a great point. And for our listeners, maybe that's the takeaway here, that there's always more to explore, always new questions to ask, even in a field like graph theory that's been studied for so long. So keep those minds curious, keep digging deeper, and who knows, maybe you'll be the one to make the next breakthrough.
That's the spirit. And on that note, I think it's time for us to wrap up this deep dive.
Yeah, I think that's a good place to stop. Thanks for joining us on this fascinating journey into the world of countable graphs and the unfriendly partition problem.
It's been a pleasure.
Until next time, keep those explorations going. All right, ready to dive deep into some graph theory today?
Absolutely. Let's do it.
Awesome. You sent over a bunch of research on this unfriendly partition problem. And just looking it over, I gotta say, this looks intense.
Yeah, it's a fascinating problem. Deceptively simple at first glance, but it gets pretty deep pretty quickly.
Well, that's what we're here for. I'm ready to get into it. So maybe let's just start with the basics. What exactly is the unfriendly partition problem?
So the core question is this. Can we always split the vertices of a graph into two groups?
Okay, so like red and blue teams.
Yeah, exactly. Like red and blue teams. And we want to do it so that every vertex has at least as many neighbors in the other group as in its own group.
Oh, okay. So it's like trying to arrange a party where everyone feels like they'd rather be hanging out with the other group.
Yeah, a very unfriendly party. And it turns out this isn't always possible.
Oh, really?
Yeah, back in 1990, Milner and Shelah, they showed that for some uncountable graphs, you just can't make this kind of partition.
Right. Uncountable graphs. So those are graphs with an infinite number of vertices that you can't even like list out, right?
Exactly. You can't pair them up one-to-one with the natural numbers.
Okay, got it. But, I mean, our focus today is on countable graphs, right? So graphs where we can at least theoretically list out all the vertices.
Yeah, exactly. And what's really interesting is that for countable graphs, this question of whether an unfriendly partition always exists, it's still wide open. Like we don't know the answer.
Oh, wow. A real mathematical mystery. So that's where this paper remarks on the countable case of the unfriendly partition problem comes in, right?
Yep, that's the one. This paper dives deep into the countable graph case, and it's pretty exciting because if we can crack this problem for countable graphs, it might give us some clues about how to tackle the general case.
Okay, cool. So there's this term alternating ray that comes up a lot in this paper. What exactly is that? It sounds kind of ominous.
Yeah, it's a specific type of infinite path in the graph. So imagine you're walking along the edges of the graph, and you're never allowed to go back to a vertex you've already visited.
Okay, so I'm wandering through this graph. Got it.
Right. Now, as you're walking, you're alternating between vertices that have a finite number of connections, a finite degree, and vertices that have an infinite number of connections, infinite degree.
Okay, so it's like I'm walking through a city, and I'm going from a big intersection with tons of roads to a quiet little cul-de-sac, then back to another huge intersection.
Yeah, that's a great analogy. And what this paper shows is that if a countable graph doesn't have any of these alternating rays, then you can always find an unfriendly partition.
Oh, wow. Okay, so that's a big result, right? Like, if we can rule out those alternating rays, we're good to go.
Exactly. It really narrows down the search space.
Okay, cool. So now we're getting to the heart of it, the proof itself. I got to say, just skimming through it, I'm already a little intimidated.
Yeah, it's a dense one, but it's incredibly elegant. To really appreciate it, we should break down some of the key tools that they use.
Okay, yeah, let's do that. Hit me with the mathematical tools.
So first up, we've got something called normal spanning trees.
Normal spanning trees, what are those?
It's basically a way to organize the graph's vertices into a tree-like structure.
So instead of this messy web of connections, we're trying to impose some kind of order.
Exactly. And each vertex gets assigned a rank based on its degree, you know, how many connections it has, and its position in this tree structure. It's like making a family tree for the graph, where each vertex has a specific status.
Okay, so it's all about creating some hierarchy within this chaotic graph. I like that. But how does this help us solve the unfriendly partition problem?
Well, it helps us approach the problem systematically. Instead of trying to color the entire graph all at once, we can use these normal spanning trees to focus on just coloring portions of the graph, step by step.
Ah, divide and conquer.
Exactly. And within those partial colorings, we aim for what are called strongly maximal colorings.
Okay, now that sounds complicated. What are those?
So these are colorings that try to maximize the number of edges connecting vertices of different colors.
So it's not just randomly coloring vertices. It's about strategically creating as much division between the two groups as possible?
Yeah, exactly. The more edges we have linking vertices of opposite colors, the closer we get to that unfriendly ideal.
Okay, that makes sense.
Yeah.
But all these different types of colorings are making my head spin a bit.
Mm-hmm.
Is there like a simple way to think about why these strongly maximal colorings are so important?
Well, one way to think about it is this. If a partial coloring isn't strongly maximal, then there's at least one edge where we could switch the color of one of the vertices and get more unfriendly connections.
Yeah, I see. So these strongly maximal colorings are like local optima. Like we can't make any small changes to make the coloring more unfriendly.
Exactly. And that's one of the things that the authors are emphasizing in Lemma 2.1.
Lemma 2.1.
Yeah, it shows just how sensitive these colorings can be to even small changes.
Oh, wow. So like changing the color of just one vertex could throw off the whole unfriendliness. That's crazy.
Yeah, it is. And that's why this lemma is so important. It's like a warning sign telling us to be careful, because even the smallest tweak can have these like cascading effects.
Okay, that's wild. So we've got these normal spanning trees to help us organize the graph, and we're trying to build these strongly maximal colorings step by step. But how do they actually put all this together to prove their main result?
Well, the proof relies on a technique called induction.
Induction. Okay, yeah, that's like that domino effect, right? If you can knock over the first domino and you know each domino will knock over the next one, eventually they'll all fall.
Yeah, exactly. So in this case, they start by proving that the statement, that a countable graph without alternating rays has an unfriendly partition holds for the simplest possible graphs.
Okay, so the simplest graphs. What makes a graph simple in this context?
These are the graphs with the lowest rank in the normal spanning tree.
Ah, right. Back to that family tree analogy.
Right. So it's like saying, okay, if we can solve this problem for a tiny little village, then we can figure out how to solve it for a whole country.
Okay, got it. So that's the base case, the starting point.
Yeah.
But what about the rest of the dominoes? How do they show that the solution extends to more complex graphs?
That's where Lemma 3.3 comes in. It proves the statement specifically for graphs where the root of the normal spanning tree, so that's like the very top of the family tree, has a finite degree.
Ah, so that's our starting point, those simple graphs with a finite degree root.
Yeah. And then comes the inductive step. This is where Lemma 3.4 kicks in. It basically gives us a set of instructions for how to take a solution for a graph of a certain rank and extend it to a graph with a slightly higher rank.
Okay, so it's like saying, all right, now that we've solved it for the village, here's how we can use that solution to solve it for a town.
Right. And to make this process even smoother, they introduce a special type of partial coloring called stable colorings.
Stable colorings.
Yeah, these stable colorings have certain properties that make them easier to extend to a full, unfriendly coloring. It's like they found a specific recipe that's guaranteed to result in an unfriendly partition.
Okay, I'm starting to see how all these pieces fit together. We've got the normal spanning tree to guide us, these strongly maximal colorings as our building blocks, and induction to help us scale up the solution. But I gotta ask, what about those vertices with infinite degree? It seems like those would throw a real wrench into the whole thing.
Yeah, you're right. Those are tricky. And that's actually where we'll pick up in part 2. We'll dive into the nitty-gritty of how they handle those more complex scenarios.
Awesome. I'm already on the edge of my seat. This is some seriously mind-bending stuff.
Welcome back. Ready to tackle those infinite degree vertices.
Oh, absolutely. I'm still a little intimidated, but I'm ready for the challenge.
Good, because this is where things get really interesting. So to deal with these infinite degree vertices, the authors break the problem down into 5 distinct cases.
5 cases. Okay, wow. Do they all have something in common, or are we talking about completely different beasts here?
Well, they're all about extending a partial coloring that we know works for simpler graphs to these more complex graphs that include these infinite degree vertices.
So it's kind of like we know how to build a house with finite bricks, but now we have to figure out how to incorporate these like infinitely large bricks without the whole thing collapsing.
Exactly. That's a great analogy. And the way they do it is it's actually quite clever. They've chosen these 5 cases so that they cover every possible way an infinite degree vertex could be connected in a countable graph without alternating rays.
Okay, that makes sense. So let's take a look at these cases. What's case 1 all about?
So case 1 focuses on a vertex with infinite degree. Let's call it W. And W has infinitely many descendants in the normal spanning tree, all of which have finite degree.
Right, so W is like the head of a big family, but all its relatives are like not very well connected at this party.
Exactly. And in this case, the authors show that you can extend the coloring by carefully selecting an infinite subset of those descendants. Let's call that subset X.
Okay, so we're picking out some of W's relatives.
Right, and we need to make sure that every vertex connected to X has infinitely many neighbors within X that are colored differently from itself.
So it's like surrounding W and its neighbors with a diverse crowd, even if it's just from within their own family.
Yeah, that's a great way to put it. The key here is that W has so many descendants with finite degree. That gives us enough flexibility to create these clusters of unfriendly connections without running into problems.
Okay, cool. I'm starting to get the hang of this.
Hmm.
So what about case 2? How's that different?
Case 2 deals with a slightly different family dynamic.
Yeah.
Here, W still has infinite degree, but it has infinitely many connections to a single descendant, V, which has finite degree.
So instead of a sprawling family tree, it's more like W has a very strong bond with just one particular descendant.
Exactly. And the strategy here is to extend the coloring in a way that ensures that W and any other vertices that have similar connections to end up with infinitely many neighbors in V's subtree that are colored differently from themselves.
It's like making sure that everyone in his inner circle feels that unfriendliness towards V's side of the family.
Yeah, that's a good way to think about it. So far, so good.
Yeah, I think so. It seems like these cases are all about carefully managing the connections between these infinite degree vertices and their descendants, making sure that the unfriendliness property holds as we build up the coloring.
Exactly. You're getting it. Now, case 3 takes a bit of a different turn. It deals with a vertex W with infinite degree where all of its descendants in the normal spanning tree have already been colored.
Oh, okay. So W is like the last one to show up at the party,
Yeah.
and everyone else is already there.
Exactly. And the challenge here is to find a color for W and to extend the coloring to any other vertices that have a lot of connections to W's subtree without messing up the existing unfriendliness that we've already established.
Oh, I see. So it's like W's trying to squeeze into this crowded room and find a spot where they don't know anyone.
Yeah, that's a good way to think about it. And to do this, the authors have to analyze the existing coloring of his descendants very carefully. They're looking for patterns and possibilities that allow them to fit W in without creating any conflicts.
So it's less about strategically choosing connections and more about like meticulously analyzing what's already there to find a compatible spot.
Yeah, that's exactly right. It's a very delicate balancing act. Now, case 4 shifts the focus away from descendants altogether.
Oh, okay, so we're branching out.
Yeah, exactly. Case 4 deals with a vertex W with infinite degree that has infinitely many connections to vertices that are not its descendants, but that have already been colored.
So W is like the social butterfly of the graph. It's got connections all over the place.
Exactly. And in this case, extending the coloring is actually pretty straightforward. Because W is already so well connected outside of its own family, they can just choose a color for W that makes sure it has infinitely many neighbors of the opposite color.
Okay, so it's like if you're already popular, it's easy to make sure you have lots of unfriendly connections.
Precisely. And finally, we come to case 5, the grand finale of this whole thing.
Okay, the climax. What's case 5 all about?
So case 5 focuses on a vertex W with infinite degree that has infinitely many connections to the subtree of one of its successors, and all the vertices in U subtree have already been colored.
Oh, wow. Okay, so it's like a combination of case 2 and case 3.
Yeah.
W has a strong connection to a descendant, but all of that descendant's family is already settled in.
Yeah, that's a great way to put it. It's the most complicated scenario they have to deal with, but the authors, they rise to the challenge. They combine the strategies from the previous cases.
I'm intrigued. How do they do it?
So first, they extend the coloring to W itself, making sure it has infinitely many neighbors in U subtree colored differently. And then they extend the coloring to any other vertices that are heavily connected to U's subtree, like they did in case 3. It's a delicate dance, but they managed to make it all work.
It's like they're master puppeteers, carefully moving all the strings to make sure everything ends up in the right place.
Yeah, that's a great analogy. So by working through these 5 cases, they've basically shown that no matter how an infinite degree vertex is connected in a countable graph without alternating rays, we can always extend the coloring while keeping that unfriendliness property.
Okay, wow. It's amazing how they've managed to break down this really complex problem into these, like, manageable chunks.
Yeah, it's a testament to their ingenuity, but we're not quite done yet. Remember, we're working with infinite graphs.
Oh, right. So we need to make sure that this process of extending the coloring, it actually reaches every single vertex.
Exactly. We can't just assume that because it works for these 5 cases, it automatically works for the whole graph. We need to make sure that this process eventually terminates, meaning it successfully colors every vertex.
Okay, yeah, that makes sense. But how do they do that? How do they guarantee that it all comes together in the end?
That's where things get even more abstract. They introduce this concept of limit ordinals.
Limit ordinals.
Oh,
Okay, now we're really getting into the deep end of math.
I know, right. But stick with me. Remember how we talked about induction, where we start with a base case and then show how to extend the solution step by step?
Yeah, the domino effect.
Right. Well, limit ordinals come in when those steps become infinite.
So it's like we're dealing with graphs that are so huge we can't even count their rank using regular numbers.
Exactly. Limit ordinals are a way for mathematicians to extend the idea of counting beyond finite numbers. They let us talk about infinite sequences and make sure that even when we're dealing with infinity, we can still use logic and build up our proofs step by step.
Okay, that's a lot to wrap my head around. But how do they actually use these limit ordinals to make sure the coloring process covers the whole graph?
So they define a sequence of stable partial colorings, each one extending the one before it. And the key idea is that for each vertex with infinite degree, the color assigned to it eventually stabilizes. It stops changing after a certain point in the sequence.
So even though we're dealing with an infinite process, there's a sense of, like, order and convergence.
Exactly. It's like those infinite decimals that eventually settle into a repeating pattern. And this stabilization is crucial because it means that even if the graph has infinite rank, which is represented by a limit ordinal, the coloring process eventually settles down and gives us a consistent coloring for the whole graph.
Wow, that's incredible. So they've managed to, like, tame infinity and make sure that the process actually reaches a conclusion.
Yeah, that's exactly right. It's a testament to the power of mathematical abstraction. But remember, all this work with colorings is just the setup. The ultimate goal is to prove that this coloring we've constructed is actually unfriendly at every vertex with infinite degree.
Oh, right. We can't forget about the big picture. So how do they tie all this back to the original problem?
That's where Proposition 3.7 comes in. It formally shows that the coloring they've built satisfies the condition for unfriendliness at every vertex with infinite degree.
It's like they're saying, look, we didn't just stumble upon this coloring randomly. We built it very carefully, and every single piece contributes to its unfriendliness.
Yeah, exactly. And the way they do it is by going back and looking at each of those 5 cases we discussed earlier. They carefully show that in every scenario, the way they extended the coloring guarantees that every infinite degree vertex ends up with at least as many neighbors of the opposite color as its own color.
Okay, that's really impressive. But are there any, like, potential pitfalls? Are there types of countable graphs where this whole proof falls apart?
You're asking the right questions. And yes, there is one crucial condition. Remember those alternating rays? The graph can't have any of those.
Right, the kryptonite.
Exactly. If a countable graph does have an alternating ray, then this whole approach doesn't guarantee an unfriendly partition. So it's a reminder that even with a proof this clever and thorough, there are still some mysteries out there.
Okay, I see. So it's like they've mapped out a huge portion of the territory, but there are still some unexplored areas.
Yeah, that's a good way to think about it. But even though it doesn't solve the whole problem, this proof is still a huge step forward. It provides a solution for a really large class of graphs, and it introduces some really powerful tools and techniques that other mathematicians can build on.
So it's not just about the result itself, it's about the doors it opens for future research.
Exactly.
Okay, phew. After all that, I think I need a breather.
Hmm.
That proof was intense.
Yeah, it was a real workout for the brain.
Yeah, it was. But it was also pretty amazing to see how they put it all together. So now that we've kind of caught our breath, I'm curious to zoom out a bit.
Yeah, let's do that.
Okay, so we've explored all the details of this proof, but I'm wondering about the bigger picture. What are the implications of this research? Why should anyone outside of, like, hardcore graph theory care about this result?
That's a really good question. And honestly, it's one that mathematicians often struggle with, you know? We get so caught up in the beauty and the challenge of these like abstract problems that sometimes we forget to connect it back to the real world.
Right, right. But in
Yeah.
this case, I have a feeling there are some interesting connections to be made.
Oh, absolutely. So while the unfriendly partition problem might seem very theoretical, it actually has some surprising links to a lot of different fields.
Oh, really? Like what?
Well, let's think about computer science, for example. In the world of networks, this problem is relevant to, how we design and optimize the flow of information.
Oh, interesting. So like understanding how to divide graphs into these unfriendly groups could help us create more efficient networks where data is routed in a way that minimizes like congestion or delays.
Exactly. It's all about finding that sweet spot between, connectivity and separation. And this problem gives us a framework for thinking about those trade-offs.
Okay, yeah, I see that.
Yeah.
That's really cool. So computer science, check. What about other fields? I know you mentioned game theory and social dynamics as well.
Yeah, so in game theory, you can think of this problem as a model for like conflict and cooperation. Imagine two players trying to divide up some resources in a way that benefits both of them, but they also have this incentive to try and outmaneuver each other.
It's like a game of chess, where each player wants to capture as much territory as possible, but they also have to protect their own pieces.
Exactly, and the unfriendly partition problem gives us a mathematical language for analyzing those strategic interactions. It can help us understand how different strategies lead to different outcomes and how those outcomes are shaped by the underlying network of relationships.
Wow, so it's like we're using math to decode the hidden rules of the game.
Exactly. And then, in social dynamics, this problem is relevant to understanding how groups form and interact. Remember that analogy we used earlier about the awkward party? Well, that's actually not too far off from how social divisions often play out in real life.
Right, right. So like cliques and polarization and all that.
Yeah, exactly. By studying the conditions under which these unfriendly partitions exist, we can gain insights into, like, how these things emerge, how these social dynamics unfold.
That's fascinating. So it's like we're using math to examine these invisible forces that shape our social interactions.
Exactly. It's really about understanding the things that bring people together and the things that pull them apart. And this problem gives us a tool for analyzing those forces in a very rigorous way.
That's really cool. So this one problem has all these connections to computer science, game theory, social dynamics. I mean, it's amazing how something that seems so abstract can be so relevant to the real world.
I know, right? It's a reminder that math isn't just about numbers and equations. It's a way of thinking about the world around us.
Absolutely. Okay, but let's be real for a second. This proof, while elegant, is also really, really complicated. Does it actually help us get closer to solving the unfriendly partition problem for all graphs? Or is it more of a niche result with, like, limited scope?
That's a fair question. And honestly, I'd say it's a bit of both. On the one hand, this proof doesn't solve the problem completely. It only works for those countable graphs without alternating rays.
Right, right. So it's like we've mapped out a big chunk of the territory, but there are still some unexplored regions.
Yeah, that's a good way to put it. But on the other hand, it's a huge step forward. It gives us a solution for a large class of graphs, and it introduces a bunch of powerful techniques that could be adapted or extended to tackle those remaining cases.
So it's not just about the specific result, it's about the tools and the ideas that it provides for future research.
Exactly. It's like this proof is a beacon shining a light on a path forward for other mathematicians who are, excited about exploring this problem. It's an invitation to dive deeper, to push the boundaries of what we know, and to see where it leads.
I like that. It's not about reaching the final destination. It's about the journey and the discoveries we make along the way.
Exactly.
So speaking of the journey ahead, what are some of the most promising avenues for building on this work? Like, where do we go from here?
Well, one obvious challenge is to try and figure out those alternating rays. Remember, those are the kryptonite to this proof.
Yeah.
So the question is, can we find a way to modify this proof, or maybe come up with a completely new approach that can handle graphs with alternating rays?
Yeah, it's like, okay, we've built this amazing bridge, but there's still this raging river blocking our path. Can we find a way to cross it?
Exactly. And that's where creativity and maybe a little bit of luck come into play. Another exciting direction is to explore those connections to other areas of math that we talked about earlier, like computer science, game theory, social dynamics. There's always more to discover. Maybe there are tools and insights from those fields that could shed new light on this problem.
Yeah, that's exciting. It's like we're standing at a crossroads, and there are all these paths leading to new and uncharted territories.
Exactly. And who knows what we might find along those paths? Maybe the unfriendly partition problem will lead us to new algorithms, new game theoretic strategies, or even new ways of understanding the complexities of human relationships.
The possibilities are endless. It's a good reminder that math is a living, breathing subject, constantly evolving and expanding.
I couldn't agree more, and I think that's a perfect note to wrap up our deep dive on. We've gone deep into this fascinating proof, we've thought about its implications, and we've glimpsed the exciting future that lies ahead. It's been a real adventure.
It has. And on that note, I want to thank you, our listeners, for joining us on this mathematical journey. Until next time, keep those minds curious and keep exploring the amazing world of math.